The distributed cache coherence protocol maintains consistency across multiple independent cache nodes through a state machine governing line ownership and visibility. Each cache line exists in one of 5 states: invalid, shared, exclusive, modified, or transitional pending. State transitions occur synchronously upon memory access requests and coherence messages. The protocol assumes a synchronous message delivery with eventual ordering guarantees. All line metadata including state, version counter, and resident node identifiers are stored in the local L1 cache descriptor. The invalid state represents a cache line that does not hold valid data. A line enters invalid state upon eviction, invalidation message reception, or initialization. From invalid state, a read access triggers a cache miss and cache fill request to the coherence arbiter. A write access to an invalid line also generates a cache fill request, but the requesting node immediately acquires exclusive ownership. Invalid lines consume minimal memory and do not participate in coherence message broadcasts. The invalid state is the default for all unallocated cache slots. The shared state indicates a cache line containing valid data readable by the owning node and potentially other nodes. A line transitions to shared upon receiving read data from the coherence arbiter when the line is not the sole owner. Multiple nodes may simultaneously hold a line in shared state. Read accesses to shared lines complete without generating coherence traffic. Write accesses to shared lines trigger invalidation of remote copies and transition the line to modified state. Shared state lines maintain a reader count for tracking dependent nodes. The exclusive state represents a cache line for which the owning node holds write permission and no other node holds a copy. Exclusive lines are acquired through explicit ownership requests and are never shared. Read accesses to exclusive lines complete locally without coherence traffic. Write accesses to exclusive lines also complete locally and do not require coherence invalidations. A line remains exclusive until an external invalidation request arrives or the line is evicted. Exclusive state implies write permission, but does not indicate whether the line has been written. The modified state represents a cache line that has been written by the owning node and contains data newer than memory. Only one node at a time may hold a line in modified state. Write accesses to modified lines complete immediately without coherence messages. Read accesses by other nodes trigger write back of a modified line to memory and transfer of ownership. Modified lines must be written back before eviction or coherence transitions. The modified state counter increments with each store operation, enabling detection of stale copies. The transitional pending state is a temporary intermediate state occurring during coherence transactions. A line enters transitional pending when a request has been issued to the arbiter, but the response has not arrived. The cache cannot process new access requests to transitional pending lines. A read request to a transitional pending line stalls the processor until the response arrives. Multiple simultaneous requests to the same line result in queuing at the cache controller. The transitional pending state typically persists for 2 to 4 network round-trip latencies. Coherence messages are generated by cache nodes and the arbiter to coordinate line state transitions. Invalidation messages request removal of copies from remote caches. Write-back messages transfer modified data to memory and the arbiter. Request messages inquire about line ownership. Response messages confirm state changes and deliver requested data. All messages include the memory address, requesting node identifier, and transaction sequence number. Messages are delivered asynchronously but preserve causal ordering for the same memory address. Duplicate messages are detected and suppressed through sequence number comparison. The coherence arbiter is a centralized component maintaining authoritative ownership information for all memory lines. The arbiter processes coherence requests in strict order and sends responses to requesting nodes and invalidation messages to affected nodes. The arbiter maintains a directory structure mapping each memory address to its current owner node and list of reader nodes. Upon receiving a read request, the arbiter grants read permission and notifies the requesting node of the current owner. Upon receiving an exclusive request, the arbiter invalidates all copies and transfers ownership. Cache line allocation follows a least recently used eviction policy. Upon a cache miss, the controller identifies the least recently used line in the target cache set. If that line is in modified state, its data is written back to memory and the arbiter before the line is invalidated. If the line is in shared or exclusive state, it is simply invalidated. Invalid lines are never written back and are always candidates for immediate allocation. The eviction process stalls the processor until the new line data is received. Memory barriers enforce ordering constraints on Coherence transactions. A store barrier waits for all previous store operations to be globally visible. A load barrier waits for all invalidation messages for previously read lines to be received. A full barrier performs both operations sequentially. Barriers are implemented by holding the processor until all pending coherence messages for affected lines have completed. Barriers increment on every cache access and are checked before new accesses proceed. The barrier implementation adds latency proportional to the number of cached lines. Write-through mode forces all store operations to be written to memory immediately, bypassing local modification state. In write-through mode, modified cache lines are prohibited. All stores generate write messages to the arbiter and memory. The cache maintains exclusive state to prevent concurrent modifications by other nodes. Write-through mode sacrifices performance for reduced complexity and is primarily used during initialization and diagnostic operations. Write-through mode is enabled through a global control register that applies to all active caches. Switching between write-back and write-through requires flushing all modified lines. False sharing occurs when two nodes cache different data that shares the same cache line. False sharing forces unnecessary invalidations and reduces performance. The protocol detects false sharing by tracking invalidation patterns. Lines experiencing frequent invalidations from multiple nodes are flagged in the arbiter statistics. False sharing mitigation strategies include padding data structures to align to cache line boundaries and using thread local copies of frequently written variables. The cache does not automatically prevent false sharing, but provides instrumentation to detect and report its occurrence. Deadlock prevention mechanisms ensure coherence requests never form circular wait cycles. The protocol employs a global total ordering of all outstanding coherence requests. Requests are tagged with a timestamp at the arbiter and processed in increasing timestamp order. Nodes process responses in the order they are received. If a node receives an invalidation while waiting for a response, the invalidation is immediately processed and the original request is reissued. This prevention scheme guarantees that all outstanding transactions eventually complete. Performance optimization through prefetching reduces cache miss latency by issuing requests before data is accessed. The protocol supports two prefetch modes, read prefetch and exclusive prefetch. Read prefetch acquires shared state without generating writer invalidations. Exclusive prefetch acquires exclusive state and is used before write operations. Prefetch requests have lower priority than demand requests and may be dropped if arbiter load exceeds a threshold. Prefetch accuracy is monitored and poor accuracy prefetch streams are automatically disabled to conserve memory bandwidth. Monitoring and statistics are maintained throughout the coherence protocol execution. The arbiter tracks total read requests, write requests, invalidation messages, and write-back operations per memory region. Each cache node maintains counters for hits, misses, write-backs, and stall cycles. Stall cycles are categorized by cause, coherence latency, arbiter congestion, or memory bandwidth limitation. Statistics are accumulated in registers accessible through the system debug interface and are cleared only through explicit reset commands. Statistics overflow is handled through counter saturation. The protocol specification concludes with initialization procedures and diagnostic support. At system startup, all cache lines begin in invalid state and all memory is assumed clean. The arbiter is initialized with empty ownership directory entries. System reset via the control register flushes all caches and reinitializes the arbiter. Diagnostic read-only access to cache state is provided through privileged instructions that do not generate coherence traffic. Self-test functions verify arbiter responsiveness and message delivery through a sequence of targeted requests and validations.